Today, we would like to discuss the training of the hidden Markov model. This is unsupervised learning. The strings which are output by the machine or observed from the machine are given, and because each output sequence can be the result of more than one state sequence, we need an algorithm for training the hidden Markov model, whereby we obtain the transition and observation probabilities of the machine or a combination thereof. So, in the last lecture we had discussed forward algorithm and backward algorithm and how to compute them efficiently. These two algorithms are used in the training of the hidden Markov model. That is why the training algorithm is also known as the forward backward algorithm, or more famously possibly as the Baum Welch algorithm. So, we proceed with the material on the slide, and I have written here HMM forward and backward algorithm, Baum Welch algorithm. So, just to remind ourselves of the forward and backward probability calculation, we remember we defined f k I as the probability of being in state S I having seen O naught, O 1, O 2 up to O k, which is the observation sequence up to the kth time step. So, this particular expression was defined as the forward probability, and the expression for that is P O naught, O 1, O 2 up to O k comma S I. So, the machine has seen up to these symbols, or the machine might have output these symbols O naught, O 1 up to O k, and then enters the state S I. M is the length of the observed sequence. So, one can write the probability of the observed sequence as P O naught, O 1, O 2 up to O m, and which is equal to sigma p from 0 to n with S p the state introduced. This is marginalization, and it can be written as the sum of forward probabilities m comma p, with p varying from 0 to n. Then we also found a method to compute the forward probability recursively from its definition itself. So, f k q is the probability of seeing k plus 1 symbols O naught, O 1, O 2 up to O k, and then being in state S q. So, this then can be broken up into two parts, the symbol the sequence itself. So, O naught, O 1 up to O k minus 1, the last symbol is isolated, which is O k, and S q remains. So, we now refer to the whole situation where O naught, O 1 up to O m is the complete observation sequence. After seeing O m, the machine enters the final state S final, which is one of the given states in the hidden Markov machine, and S naught is the starting state. So, as is shown in the output and state sequence, the transitions are state to state with a particular output symbol shown on top of the arrow. So, we see that this O k S q is there in the expression, and then we introduced S p, and this is marginalization, p going from 0 to n, sum is also introduced. So, now we have this pattern here S p O k S q. So, this is the pattern which exists in the observation sequence state sequence. So, we isolate this part probability O naught to O k minus 1 with S p, this part is isolated. This is then multiplied by the probability of O k S q given O naught to O k minus 1 and S p. This is nothing but the chain rule, and in the next step the only conditioning factor S p is retained, nothing else affects this probability of the observed symbol OK at the next state S q, and therefore, we drop this whole sequence O naught to OK minus 1. Now, P O naught to OK minus 1 with S p is nothing but the forward probability F k minus 1 P, and P OK S q S p is written as the transition S p to S q with OK as the output symbol. So, this whole probability F k comma q is nothing but sigma F k minus 1 P, P going from 0 to n, and each F k minus 1 P is multiplied by the transition probability P S p to S q with OK. So, this whole deduction is completed by applying marginalization here and then chain rule here and the Markov assumption after that. Okay. Marginalization, chain rule, Markov assumption, and this produces the recursive expression for F k q. And it is easy to see that F k q can be looked upon as the sum of the feeding probabilities F k minus 1 P multiplied by the transition probability. And each of these can in turn be computed from F k minus 2 and another index let us say t varying from 0 to n, and this way the whole computation can be completed. The boundary condition for this comes from the initial probability F 0 and P, where O naught is the symbol seen, which is nothing but epsilon, and having seen epsilon, what is the state. So, these are the initial probability values of the states, the probability that the machine is one of these initial states. So, this is the way F is computed from output sequence, state sequence, and the expression for it. Similarly, we could compute the backward probability B k comma I. We remember B k comma I is defined to be the probability of seeing OK, OK plus 1 up to O m, given that the state was S I. Okay. So, B k comma I is nothing but probability of OK to O m given S I, with m as the length of the observed sequence. So, from this definition it is clear that probability of the observed sequence is nothing but the probability of the observed sequence given the initial state S 0. So, this is nothing but B 0 0. Okay. So, the first 0 is the starting index of the sequence we will observe until the end, and the second 0 is the state in which the machine is before this observation sequence is seen. So, again we have a recursive way of computing B k p, where k is any index within the observation sequence, and we can recursively compute this. So, since this is backward probability, we will gradually look into the smaller and smaller segment of the observation sequence towards the end. Okay. So, naturally k will now increase in its value one by one. So, let us see how the process is. P OK, OK plus 1 up to O m given S p. This is isolated now, we take up OK separately, and OK plus 1 to O m is the shorter sequence. So, this is OK plus 1 to O m with OK given S p. We introduce the variable state S q as is seen in the picture here. S p was the starting state before OK to O m was observed. S q is the starting state before OK plus 1 to O m was observed. So, now we have P OK plus 1 to O m with S q, and this can now be used, and P OK S q given S p is isolated. Now, on marginalization, now on chain rule, we have to have the term P OK plus 1 to O m given OK, S q and S p. Now, the only conditioning factor for this term is S q. So, OK and S p can be dropped, which is dropped, and the term that we have now is P OK plus 1 to O m given S q, P OK comma S q given S p. So, this can be written as B k plus 1 comma q PSP to SQ with OK as the output symbol. Okay. So, therefore, we have again like forward probability a backward probability expression recursively computed from shorter segments up to the end of the sequence. Here also the boundary condition is obtained from the final symbol OM, the state before OM and the final state. So, these probability values have to be given. Again, this backward probability can be computed in linear time proportional to the length of the sequence for which the probability backward probability is calculated. So, both backward and forward probability can be calculated in linear in the length of the sequence. Now, both these probability values are very useful for various kinds of computation involving hidden Markov model, and we will now proceed to see how these two probability values are used for training the hidden Markov model. So, we come to this topic of HMM training, the algorithm known as Baum Welch or forward backward algorithm. Now, to understand this algorithm, we will first clear up a notion of counts of transitions with output symbol within the sequence which is produced by the machine. Let us suppose that ABB, AAA, BBB, AAA is the sequence which is produced by the machine shown above. Now, this is a machine where all transitions are possible, and therefore, given this observation sequence, many states are possible which produce this output sequence. So, one of the output sequences is shown here Q to R A. So, the machine goes from Q to R on A, and from R on B it comes back to Q. Then from Q it takes a B and remains in B. It could have gone to R also, and then from Q to A it goes to R, Q to R it goes with A, and then R it comes back to Q with A, Q to R again with A, R to Q again with B, and so on. So, this is the whole state sequence which is produced corresponding to the observation sequence, all of whose symbols are written on top of the arrows. Now, when this sequence is given, we can make a frequentist approach to probability calculation. So, for example, the probability of Q going to R on A or with A is found out to be 5 by 8. Okay. How do we get this value? So, we make a record of the transitions and the corresponding output symbols as they obtain in the output sequence. So, we find that in the output sequence and the corresponding state sequence, we have the transition source to destination Q to R with the symbol A. This happens 5 times. Okay, this happens 5 times. Now, to get the probability value of Q to R on A, we have to find out what other transitions from Q are there in the observation sequence. So, we find that there is transition from Q to Q with the symbol B. So, these are the only 2 cases of transition from Q with Q as the source. Okay. So, therefore, it makes the total count of transitions where Q is the source state as 8, 5 plus 3 8, and out of that Q to R with A is 5. That is why the probability of Q to R with A is nothing but 5 by 8. Similarly, probability of Q to R with B, it should be Q to Q with B is 3 by 8. So, in general, the probability of a transition from S I to S j with symbol W k is the count of S I to S j with W k, number of times this occurs, divided by all the total number of transitions from S I to any state with any symbol. Okay. and here we have shown the index to be going from 1 to A, where A is the alphabet symbol and this is W m, okay, all possible symbols, and L from 1 to T, where S L is the destination state and T is the number of states. All right. So, now the point that is being made is that if we have a single output sequence, single state sequence corresponding to an observation sequence, then this kind of taking the count is all right, this is valid. But if there are multiple state sequences for an observation sequence, what do? We have a number of state sequences for an observation sequence. So, the idea is to weight these counts, okay, to prorate or weight these counts with the probability of the state sequence given the observation sequence. So, you would like to write this expression and explain with the formula. So, suppose there is a state sequence S and the observation sequence is W, and suppose a pattern S I to S j on W, okay, appears in this. So, the count of these we are saying will be as follows. So, the count of S I to S j on W will be found by weighting the number of appearances by probability of S given W, which sort of makes sense, because now we have the number of these patterns obtaining in the observation sequence and the state sequence, and if this pattern appears in multiple state sequences resulting from the observation sequence, then it makes sense to give weightage to these counts, okay, give weightage to these counts, and the weight comes from the probability value of S given W, S given P S given W, and if the pattern appears in S, then that count will be multiplied by the probability of P S given W. Okay. So, this is intuitively acceptable, and this is the way we would like to obtain the count. So, going to the slides once again, let us illustrate this procedure of computation. So, P S I to S j on W k is nothing but C S I to S j on W k divided by total number of count of transitions from S I to S L on symbol W m, where this is the count of all those patterns where S I is the source, and any W m and any S L are the corresponding output symbol and destination state respectively. C S I W k S L, that is the count of this pattern, is obtained by finding out the number of these patterns S I W k S j in the context of the state sequence 0 to n plus 1 and the observation sequence 0 to n. So, this is the context in which we are seeing this pattern, and this is the number. We weight this number by the probability of the state sequence given the observation sequence, and we have to take this expression for all possible states which result from this observation sequence. That is why there is a sigma of all possible state sequences S 0 to n plus 1 given the observation sequence. So, this is a nice intuitive formula, the count multiplied by the probability value, and these the probability is found from this count, the count is found from the probability value. So, the way the method starts is that we first assume some probability values of these transitions. From there we obtain these count values, from there we obtain these count values. From this probability of transition we can very easily compute P s given W. This is nothing but the Viterbi algorithm, and for bigram sequences this is nothing but the multiplication of the transition probabilities. So, we obtain this count, and from the count we obtain the new probability value. From the new probability value we obtain the new count, from the new count we obtain the new probability value. This is the way the computation proceeds, from probability to count, count to probability, probability to count to probability. And eventually after some time the algorithm terminates when we see that there is no appreciable change in the probability values. Okay. This algorithm is called expectation maximization. So, we expect a value for the count and then maximize the probability of the observation sequence through this. All right. So, this is the basic idea, and these are the two controlling equations. We illustrate this procedure with this example here. Here is an HMM, where the two states are Q and R. The transitions are on A and B. It is shown that from Q to R, a transition can happen with a probability of 0.67, where the output symbol is A. And from R to Q, the transition is on B only, and this is a certain transition, there is no non-determinism here. So, the probability is 1.0. From Q we find that apart from transition to R on A, we also have transition back to Q on B with probability 0.17 and back to Q on A with probability 0.16. So, this is the machine which is given to us, and we have to learn this machine. Now, let us be careful about the meaning of learning here. You would like to write certain important comments here. So, the Baum Welch algorithm, Baum Welch learns the probability values on arcs, not the structure of the HMM. This is important to remember. This is imp. Okay. So, we never learn the structure of the machine. We learn the probability values on the arcs. So, this is an important point in whole of machine learning. It is very rare that we learn the structure of an automaton or the context free rules of a probabilistic context free grammar. What we learn are the probability values corresponding to the elements of the machine, okay. And the structure is a priori given. Learning the structure and then learning the probability, that is known to be a difficult problem, that is seen to be a difficult problem. The structure learning does not happen in such cases typically. We learn the probability values, and the way we learn this is being shown here. So, then it is clear that we are given this machine, the transitions are given A, B and so on. For example, we know that from R a transition is only possible to Q, and that too only with the symbol B. All right. But we do not know the exact probability values. This is our problem. We need to learn this. So, initially we start with a guess for the probability values. So, we see that from R to Q only one transition is possible, which is on B, and we give it a value of 1.0. We know nothing about the transition probabilities on B and A here and this A here. So, the probability values are assumed to be 0.48, 0.48 here, and this should be actually 0.04, only that will make the total probability value equal to 1. This is 0.04. I would like to correct it sometime, and these probability values are the initial estimates. With these initial estimates, let us see what we can do. So, now the probability of the path given the observation sequence, which is nothing but A, B, A, this should be B, B, A, B, A, B, B. Okay. So, A, B, epsilon to A is the first observation, then A to B, B to A to B, and B to B. So, the whole sequence is actually A, B, A, B, B. And this we know how to find the probability of. We simply multiply the probabilities of the transition. So, epsilon to A on Q, we know the probability, A to B on R, we know the probability. So, we simply multiply these probability values. We can make a check and against the machine which is given to us through initial guess, and once we do that, we find that the probability of the path is 0.00077. So, this gives us the first factor of this expression P S naught n plus 1 given W 0 to n. This n is the count. Now, we can see that the number of times this transition happens Q to R on A. So, Q to R on A happens here, Q to R on A happens here also, and no more. So, there are two such appearances of Q to R on A. So, we have to multiply the probability of the path given the observation sequence, which is 0.00077 by 2, and get the new probability of Q to R on A as in this state sequence with respect to this state sequence and this observation sequence as 0.00154. We have to get this expected count through the computation of all the states. So, 4 such state sequences are possible. Here the probability value is 0.00442, the probability of the path, and Q to R on A appears only once. So, this is multiplied by 1 and we have 0.00442. In this case also we have the path probability as 0.00442 and Q to R on A appears only once. So, multiplied by 1 0.00442. The probability of this path sequence is 0.02548. Q to R on A does not appear here. So, this is 0, therefore, path probability into count gives me 0. I have to sum all these probabilities and having taken the sum and having rounded it to 2 places of decimal, we obtain the new probability value as 0.01 or the new count, expected count, the expected count of Q on R, Q to R on A as 0.01. Similarly, we can find out the expected count of R to Q on B from here 0.01, then Q to Q on A as 0.06, Q to Q on B as 0.095. So, these expected counts of various patterns have been found out corresponding to this observation sequence. So, next what we have to do is that we have to normalize these counts to get the probability values as given in the formula to get the new probability values. So, this is nothing but Q to R on A and then Q to Q on A and Q to Q on B. So, these counts are taken and put in the denominator. So, 0.01 divided by 0.01 which is itself 0.06 which is nothing but this and 0.095 which is here. So, when we divide 0.01 by these normalizing counts, we get the probability value as 0.06. So, we started with the initial probability Q to R on A, Q to R on A as 0.48, we have to reach a value of 0.16. So, this has to reduce. Q to R on A, Q to R on A, we started with 0.04 and we have to reach a value of 0.67. So, it has to increase and we find that it has increased. It was 0.04, now it has become 0.06. The probability of R to Q on B, there is no other transition from R and therefore, it has to be divided by 0.01 itself and we get the value 1. The Q to Q similarly is normalized and we get the new probability as 0.36 and the new probability for Q to Q on B is 0.581. So, this is the new probability value after we have seen the observation sequence A B A B B, and if this was the only observation sequence, then after the first iteration these are the new probability values. Okay. And from these new probability values, we will again be able to compute the new path probabilities. From the new path probabilities, we will get the new expected count here and then we will obtain the new normalized values, which will be new probabilities again. So, this is the main idea of the algorithm. You must have observed how probability of the sequence, how the probability of the sequence gets recomputed from the new probabilities and these give rise to new expected counts. New expected counts give rise to new probabilities. Okay. So, what has been illustrated is just one iteration over one observation. The question that arises now, which I would like to write, is if multiple observation sequences are given, how to run the Baum Welch algo. Okay. So, what we do is that we find the values of new probabilities over each observation sequence, get the new probabilities for each observation sequence, do this for one iteration, get the values after one iteration over all observations. This is called an epoch. So, let us write this definition here. Epoch is nothing but one iteration over all observation patterns. One iteration over epoch is nothing but one iteration over all observation patterns. So, after each iteration we get the updated probabilities. This is done until convergence. So, I hope this gives you a correct idea about how the computation proceeds. Now, let us understand the theory of the Baum Welch algorithm. The procedure was illustrated by this example. Let us understand the theory. This is the computational part and we will understand the mathematical expressions involved in this. So, our term of interest is C S I going to S j on W k. S I is the source state, S j is the destination state and W k is the observed symbol. We are supposed to get the count of this pattern S I to S j on W k in the context of the state sequence and the observation sequence. So, this is a number, we have to multiply it or weight it by the probability of the state sequence given the observation sequence, as has been understood. and this task has to be done for all possible states that results from the observation sequence. Now, this part P s given O can be converted into P s given W can be converted into P s W, it is a joint probability, and we have to divide it by probability of W, the observation sequence, and this W does not depend on S, and therefore, this is taken out of the summation symbol. Now, we have the expression where we have the state sequence, observation sequence, state sequence, observation sequence here, and the pattern that obtains. Now, one can see that this whole number of the patterns can be converted into an equivalent expression of the probability of the tth state being S I, t plus 1th state being S j, and the tth observation symbol being W k. Okay. So, this whole pattern S I to S j on W k is equivalent to S t being S I, the tth state being S I, t plus 1th state being S j, and the tth observation being W k, and this happens in the context of the state sequence S and the observation sequence W. So, previously itself there was this summation over all possible state sequences. Now, we introduced the summation over all possible t, where t is varying from 0 to n, which is nothing but a position. T records a position in the output in the observation sequence. So, you can see that this number, this expression with the count with the number of the pattern is equivalent to this expression, where the pattern is searched for at every location of the output sequence or the observed sequence. So, these two expressions are equivalent, because wherever I do not see this pattern, the probability will be 0. Otherwise, there is some probability which is equivalent to this expression. Now, what we can do is that since S 0 to n plus 1 is present here as a joint probability expression, and since there is a sum over all possible state sequences, this particular variable can be dropped by the law of marginalization. And having dropped it, we have the pattern, have the probability expression here with source state S I at tth location, S t plus 1th state is S j, the tth observation symbol is W k, and the whole observation sequence is W 0 n, and we have a multiplying factor of 1 by p W 0 to n. Okay. So, this is the expression we have, and this can be picturized by means of the observation sequence here W 0 to W n and state sequence S 0 to S n plus 1. Now, we look at the expression P S t equal to S I, S t plus 1 equal to S j, W t equal to W k and W 0 n. So, here again we can make use of isolating parts of the string that are useful to us and applying marginalization, chain rule, Markov assumption, etc., to get a useful expression. So, the way we work is that we isolate the part 0 to t minus 1 as the observed sequence, and with the state S t being S I. So, this part is isolated, so that we can have a forward probability up to the tth location, and then S t plus 1 being S j, and the observation sequence from W t plus 1 to n. This will be useful to us in terms of the backward probability, and W t is equal to W k. We have also done one thing, that we have isolated this pattern here S t equal to S I, S t plus 1 S j and W t equal to W k, which should give us something like a transition probability. Now, we apply chain rule and we see this expression here. The summation remains t equal to 0 to n. So, P w 0 t minus 1 s t equal to s I is isolated. This will give us the forward probability. When I isolate this, I have to apply the chain rule and say that P s t plus 1 equal to s j, w t equal to w k, and w 0 to t minus 1 comma s t equal to s I. So, this is nothing but a destination state, observation symbol and source state, and this is a string up to this particular observation symbol and can be ignored because of the Markov assumption. So, this part will give us the transition probability. What remains is this part w t plus 1 to n, which is the observation sequence starting from t plus 1th location to the end of the string, and this again by chain rule has to be conditioned by s t plus 1 equal to s j, w t equal to w k, s t equal to s I, and w 0 to t minus 1. Okay. All these will come as conditioning variable for w t plus 1 comma n, and we know that w t plus 1 to n, which is the observation sequence from t plus 1th location to the end of the string, is dependent only on the state which existed before this observation sequence, and that is nothing but the t plus 1th state as s j. So, in the conditioning part we retain only this. So, from this expression we see that the first part gives us the forward probability f t minus 1 I, the second part gives us the transition probability p s I to s j on w k, and the remaining part gives me the backward probability b t plus 1 comma j. So, this is the forward probability up to the tth location in the string. This is backward probability from t plus 1th location to the end of the string, and in between is the transition probability p s I to s j given w k. So, this is a neat expression which is obtained the expected count of a particular transition. So, the expected count, if you remember, is C s I to s j with w k. So, in the context of the observation sequence and the state sequence, we have the expression as expected count is nothing but t going over the whole string, and we have to sum these quantities, and f t minus 1 comma I, this is the forward probability, the transition probability and the backward probability. The whole thing of course, has to be divided by the probability of the observation sequence. Now, probability of the observation sequence also can be expressed as the product of forward probability and backward probability with t varying over the whole string. So, you should try to show this. I write down the expression here. So, it can be shown that probability of the observation sequence 0 to n is nothing but t equal to 0 to n f t minus 1 I into b t plus 1 j. Okay, and the picture is s I to s j on w k. So, this means that we can completely work with backward and forward probabilities, and these backward and forward probabilities can be computed in time proportional to the length of the sequence in question. So, this is a neat expression where we get the probability value, where we get the expected count from this formula, of course, dividing it by the probability of the observation sequence, and from that count we can obtain the new probability values. Then the probability values can be used in the forward backward formula to obtain the new count. This will give rise to the new probability value, and this will go on. So, as this goes on, we finally come to a situation where the probability value does not appreciably change, and that would be the termination of the algorithm. So, there are some interesting points about this algorithm. Some of these issues pertain to the behavior of the algorithm when it gets stuck in a local maxima, for example. So, in this particular algorithm the computation stops when there is no appreciable change in the probability values. Now, this particular state of probability values can be a case of local maximum. Okay. Given this particular initialization, we could we come to a sort of dead end, I would say, because the probability values do not change anymore, but it is very possible that these probability values are not the desired probability values. It is a case of local maximum or local minimum, however way you want to look at it, and this can be changed only by reinitializing the machine and starting the computation all over again. So, this phenomenon is the phenomenon of getting stuck in the local minimum. Looking at the slide once again, we see there are two other points which can sort of handicap the algorithm. One is the issue of symmetry breaking. So, the symmetry breaking issue is that if we do not randomly initialize the weights, but a kind of symmetry exists, which is shown here. You can see that A value, B value and A value, B value here. So, forward and backward transitions with A and B values, they have equal starting probabilities. Now, if the incrementation happens with equal amount, then these values will never be different, and if the target machine has different probability values, it will not be possible to reach them. And the final problem is the label bias problem, which we will discuss later. If one of the probability values dominates, then it can lead to problems in the computation. So, this is the Baum Welch algorithm, which is an important algorithm in this area of probabilistic models, hidden Markov model in particular, and this is a very useful development.